So we have airflow in a 2.5 centimeter diameter pipe at high velocity, so the Reynolds number is very large. The roughness of the pipe is 0.025 millimeters. Determine the friction factor. So find the friction factor. I'll pause and let you work on that for a minute, okay? Okay, so since it says that the Reynolds number is very large, you kind of have in your mind that image of the Moody diagram. It's out in this region where it's flat, the friction factor is only a function of the relative roughness. So we calculate the relative roughness and we find it's 0.001. You go to a pretty good Moody diagram, whatever Moody diagram you have in the textbook, you look for 0.001, that's that curve. Look for out in this region, come across 0.02 was 0.02. Here's another problem. So we have water at 5 degrees C, and at that temperature, its viscosity is temperature dependent, so that's more important, but there's a density of 1,000 kilograms per meter cube. It flows steadily through a 3 millimeter diameter, 9 meter long horizontal pipe with an average velocity of 5.1 meters per second. Calculate the head loss, the pressure drop, and the minimum pumping power required to overcome this, Wdot, the minimum fluid pumping power. Let you work on it for a minute. Okay, whenever you have the head loss or pressure loss, in your mind you can think of that equation that it's the friction factor, length to diameter. You just unravel the friction factor, the definition of the friction factor, then you unravel it. And it's times V squared over 2G for head loss, or it's the same friction factor, same length to diameter, over 1/2 rho V squared if it's for a pressure loss. So the F is the same in both of these equations. The L is the same. The D's are the same. It's just what I put in the parenthesis right here. I should have got rid of those red underlines to make it more clear. It's whether or not this is V squared over 2G or it's 1/2 rho V squared. So you're talking about energy per unit volume, or you're talking energy per unit weight. But that's the measure of the mechanical energy. Yes, sir. All the other terms are there. The length, the diameter, the V squareds are given to us, and we know G if we need it. But F, how do I get F? Okay, I'm thinking in my mind Moody diagram. Lower than 2,000, I have an analytic expression for the friction factor. Above in the turbulent region, I may need to use a correlation or just use the Moody diagram, so I need to find F. So I calculate the Reynolds number for this problem. The Reynolds number, rho V D over mu, and I find that the Reynolds number is 10,070. What does that imply? Turbulent. Did they give me any roughness of the pipe? What do you want to assume? Smooth. We have a lot of smooth pipes in application. See, you're stuck. You have to make an assumption there. So you look at the Moody diagram and you find that the friction factor is about 0.03. So you go to the head loss equation that I wrote up there. You have 0.03. You have the length of the pipe, which was 9 meters. You have the diameter, 0.003 meters. You have to get the lengths both in meters, right, so that they'll cancel. Times V squared, which is 5.1 meters per second squared, divided by 2 times 9.81. And we find that that head loss is very large, 100 and almost 20 meters. Yes, sir. Well, I would, if I needed you or wanted you to use the Moody diagram, I'd provide that in the exam. I could give you the Colebrook equation, but it's implicit to find F, and you've got to iterate. Oh, great for implementation, but not on exam. You know, implement it in MATLAB or some other software, but not in a timed exam. you can get that pressure loss. It's 1170 kilopascals. Once you have that, all you had to do was multiply rho G times H of L, and that gives you the pressure loss. The last part, what's that minimum pumping power? Well, the minimum pumping power is Wdot min would be the pressure loss times the volumetric flow rate, AV. They give you the diameter, so pi d squared over 4, the velocity, V, get it cubic meters per second, multiply through, watch your units, and you get that the minimum pumping power is 42.2 watts. Now, why did I leave the whole side of the page over here blank? Because in an earlier problem, everything was the same except for the velocity was given to be 90 centimeters per second. The same fluid, the same diameter, the same length. And when we solved that problem, we found that the Reynolds number was 1776, right? So because the boost of the velocity is 5.7 times larger for this new case where I have the velocity of 5.1, almost 6 times larger. The Reynolds number is 5.7 times larger. Okay, but what about the friction factor? Well, we took the friction factor 64 over Reynolds number, and we found the friction factor for the case to be 0.0036, right? Well, compare those two friction factors. This is 83% of the previous one, of the laminar. The turbulent is not even 100% of the friction factor for the laminar. So just looking at the friction factor, you have to multiply by the L over D and then the dynamic head, or the dynamic pressure, or the velocity head, or the velocity pressure, okay? Something like that. So I'm just trying to compare them. Okay, let's continue down. We found that the head loss for the laminar was 4.46 meters. I know that's too many digits, but take a look. How did that head loss compare? Well, it's 26 or 27 times greater. You know, it's 27 times 4.5 to be 120. So you went up 5, nearly 6 times, not even 1, you know, it's 0.8 times. Now it's 27 times. The same with the pressure loss. And when you calculate the power we calculated was 0.28 watts, and it comes over here and it's 151 times. The power is a lot more because the power is a product of the pressure drop as well as a product of the volumetric flow rate. So V went up, and so it affected the volumetric flow rate as well as the pressure drop. Okay. Yes. I think they're unraveling the 64 over Reynolds number. So let me do that. Insert a new page. Whoops. And so let's say somebody says the friction factor is 64 over Reynolds number. That implies it's laminar flow. And then they'll unravel that friction factor. That's the head loss times 1/2 or V squared over 2G, okay, is equal to 64 over rho V D times mu. And so you'll get head loss. You can get this. You get 64. Let me just do it slowly. Rho VD. You'll have V squared over 2G, and you'll have L over D. Okay, so I dropped this down to 32. because of this and this. And then I'll have the viscosity mu. I'll have only one V because these cancel. And I'll have the L. Then I'll divide by rho G d squared. So sometimes you'll see an equation like this and you say, ooh, hey, let's just use this equation. Well, it's for laminar flow only, and this problem was not laminar flow. I'm sorry, what? Yeah, this is circular. And this whole equation is for a laminar. And if you have laminar flow in, let's say, a square or something else, maybe it's 59 or 58 over the Reynolds number. Or if they have a whole table of them, an ellipse with a certain ratio on it, they'll give you that constant value. It'll be maybe 55 or 52 or 48. It won't be 64. But if it's a round pipe, the constant is 64. Yes, right. Use the hydraulic diameter for everything that's not circular. So now I want to talk about the modified Bernoulli equation. We had a Bernoulli equation and it was along a streamline, but then we wanted to do it and use it for pipe flow. And inside of pipes being connected, you could have not just elevation change and velocity change and pressure changes, but maybe you had something that put energy into the system. Maybe you had a pump. And so we would have a pipe, it'd be like this, then you have a pump and it'd go like that, I don't know, go like this and back again, right? And we modified our Bernoulli. We said maybe at state 1, pressure 1 plus 1/2 rho V1 squared plus rho G Z1. And then if you had a gain, some pressure gain, maybe due to a pump. True? And then over here you have the pressure at 2, here's state 2, the outlet 1 to 2, plus 1/2 rho V2 squared plus rho G Z2. Now what we can do is we can put some losses, pressure losses right there. And those pressure losses we can model by these friction factor, length to diameter, 1/2 rho V squared. Now you say, I have this section of pipe here, section 1, then section 2, then section 3, then section 4 and 5 and 6 and 7, etc. So if you have, each section could have its separate friction factor. Now, each section has the same diameter, same type of pipe, the relative roughness, same mass flow rate. Well, they're not going to have a different friction factor. Okay, but some cases, in general, it could have different lengths, different diameters, different velocities, different friction factors, and you would sum them up over all the sections to get the total pressure loss due to the friction through the straight runs of the pipe. See that? So now you can modify Bernoulli with head loss. So you have a modified Bernoulli equation for the head loss. Well, not only can you now account for the straight run of pipe and the losses associated with it, those losses, just reminder, you want to put it in the pressure loss, F, L over D, 1/2 rho V squared. Okay. Those are called the major losses. Major, not because they're always the dominant losses, but because historically they were the first dealt with. They just call them the major. Compare them with the minor losses, which are due to fittings and valves and restrictions and other things. They're the things that connect the straight run pipes and then go in between the straight run pipes, okay? Think of valves, think of elbows, think of fittings. And how do we model those? Well, we model them not with a friction factor, F. We model them with the loss coefficient, K sub L, subscript L, K subscript L. And that K subscript L is defined as the head loss divided by V squared over 2G. Okay, so I could have written over here the head loss is equal to the friction factor, length to diameter, V squared over 2G. Instead, if I did pressure loss, energy per unit volume, or head loss, energy per unit weight. Okay. So if I unravel this equation, I get that the head loss for minor losses for fittings is equal to the loss coefficient K sub L times V squared over 2G. Well, we compare, and that loss coefficient has the same effect or factor as the friction factor times length over diameter. And sometimes people will even come up with an equivalent length for the minor losses. So can you just see if you equate these? The length equivalent, UIV, is equal to the loss coefficient times the diameter divided by the friction factor. And sometimes that's useful in comparing where do you have the restriction in the system. But this really only works when the friction factor is, how do I say it, in the fully turbulent region, where it's not a function of Reynolds number anymore, it's just a function of the relative roughness. It's a constant. It's not a function of Reynolds number. And then it works better. But if the friction factor is a function of Reynolds number and relative roughness, probably don't use the equivalent length. Just stay away from it. But you'll see the equivalent length out there a lot. Okay, and it's helpful to compare. Okay, so now we have the total head loss to modify the Bernoulli equation. What does this look like? The sum of all the straight runs, all the major losses. This is the sum of all the minor losses, any valves and stuff. So if I go back to this problem, maybe I had a 90-degree elbow. Maybe I had a 90-degree elbow. Maybe I had, I don't know, another 90, another 90, another 90, another 90. Or maybe I had a restriction. You know, maybe I had a device that I had right in here, and it had a big restriction, or it was a valve, partially closed valve. So that would be a minor loss for that component. And you could then put it into this total loss, either in pressure or head. Modified Bernoulli, in head, you have H1, it's a P1 over rho G plus V squared over 2G plus Z1 plus any head gain equal to P2 over rho G plus V squared over 2G plus Z2 plus any of these losses, which I would just be writing that equation that I have on the other page, both the majors and the minors for your losses. The sum, okay? If you want, I'll just write it out. It's the sum of the friction factor L over D V squared over 2G's plus the sum of the KLs V squared over 2G's. And you put a lot of subscripts. Sum over all the I's, sum over all the J's. How many straight runs you have, how many fittings you have. Can you see how useful this might be to mechanical engineers designing fluid flow systems? Very useful, very useful, right? So there's your total head loss. A valve causes 2.2 meters head loss. So head loss is equal to 2.2 meters. Is that delta PL or HL? HL. Because look at the units, meters. When the average velocity of the flow, V, is equal to 4 meters per second. What is the loss coefficient, K sub L? I'll pause and let you work on that. All right, so we solved this problem. We found it was 2.7, and the The loss coefficient, I always like to ask, what are the units on that loss coefficient? Students always, oh, what is that? And then it's dimensionless. There are no units, right? You have to work through it yourself. How did you calculate that? How did you calculate it? Yeah, that's right. So I would think like this. Head loss is equal to the loss coefficient times that velocity pressure, but it's not pressure, velocity head, and that's G. So case of L is just HL 2G divided by V squared. Work through your units and you'll get it. True? How many people did it that way? Everybody. Good. Pipe inlet loss coefficient. There's a number of different types of ways to get pipe flow started. You could have a nice sharp-edged corner. You could have a smooth round corner to the pipe with a different radius of curvature, or you could have the pipe protrude into the tank and then take off. Okay? What you got to think about is little fluid particles that are eventually going to go toward and into the pipe. And especially the fluid particle here, this one just goes straight in. This one's got to turn. And whenever they turn, they like to not follow the surface of the wall. And they'll open up and there'll be a little recirculation region right in here. That recirculation region isn't an area where the flow is going down the length of the pipe. It's just recirculating right in there. It feels like it's restricted right here. And so they'll have a loss coefficient for the entrance, KL, and maybe it's 0.5. Now, if you have it smooth, just put the dots of fluid that are eventually going to go. This one, straight in, no problem. This one, can you see that smooth wall is going to help navigate and get in there? It's going to have less of a problem of any separation region. And so the loss coefficient here is much lower. Maybe it's down in the 0.03 region, but it really depends on the radius of curvature, right? Some lowercase r compared to d or something, or 2r right in here, okay? Some relative, that radius. Now, what about this one? Well, put your cloud of points, the fluid, all around. This one again is just going straight in. What about these over here? What about this one over here? He has to do 190. What do you think? Or not a 190. Come on, professor. 190. What is that? But it makes it even harder. So do you think the loss coefficient would be greater? Yeah, 0.8 versus 0.5. Now, those are in tables of the textbook, the loss coefficients. Okay. One thing I forgot to mention about on the Bernoulli equation is a lot of times when you went from along a streamline to in a pipe, they would put an alpha right there, an alpha right there, an alpha right there, an alpha right there. What are those alphas? That's right, kinetic energy correction factor, because this is the average velocity in the pipe. And the kinetic energy correction factor works. Now, if it's turbulent flow, and most of our problems are turbulent, what do you think alpha is close to? 1.02, 1.05. It's close enough to 1 to just say it's 1. Okay? But if it's laminar flow, guess what alpha is? Now, we just don't have a lot of cases where you have a lot of laminar flow. And if you do have laminar flow, guess what? The kinetic energy isn't all that important in laminar flow because it's slow-moving flow. And so the pressure here and the P's are big, and maybe the rho G's are big, rho GZ's are big, but typically this term is small. So a lot of times I don't even write that alpha in there, because if it's going fast, yes, the speed is high, yes, that kinetic energy is appreciable, but alpha is close to 1, it's turbulent flow. And if it's small, if it's laminar flow, the Reynolds number is small, the velocity is small, the kinetic energy component is small. So even if I have alpha equal to 2, I could probably neglect the whole term anyway. Does that make sense? But you'll see that alpha, that kinetic energy correction factor in there, and you'll think, oh, sometimes it's 2. I have to pay attention. Well, it's 2 when it's laminar, when it's negligible. You'll have pipe outlet loss coefficient. If I have, I'm taking a pipe and I'm dumping it into a big tank like this, and the fluid level's up here. When I come through the pipe, let's say I'm at section 1, and then I go into the pipe, let me take it all the way up here to section 2, okay, point 2 or location 2. At 1, if I look at it, I have pressure 1 plus 1/2 rho V1 squared plus rho G Z1 equal 2, and then I'll have pressure at 2 plus 1/2 rho V2 squared plus rho G Z2 plus some, I'm going to call it head loss due to the exit into the pipe loss coefficient. And that's going to be a loss coefficient times 1/2 rho V1 squared. It's the speed that it's exiting. That's the speed at 1, right? It's not the speed at 2. What's the speed at 2? What's the speed here? 0. That's 0. Negligible. Okay. So what happens is the book talks about saying the loss coefficient for an exit is equal to alpha. Because when you're exiting right here, it just gets dissipated. What's the kinetic energy at state 2? 0. Did it have kinetic energy at state 1? It sure did. It was alpha times 1/2 rho V squared. All right. I'll tell you what. If you take the streamline all the way to 2, I wouldn't necessarily tell you to include the loss coefficient for that exit. It's already included in the modified Bernoulli equation, because right here it's has that kinetic energy in it. Over here there's no kinetic energy. Okay? But if you want, you put it in there, and you put in there the alpha, or let alpha be 1, the loss coefficient's equal to alpha, or the loss coefficient's equal to 1 for the exit. Make sense? All right. So, I guess just put it in. It's not that big of a deal. Sudden expansions and contractions. We talked about going into a pipe from a very, very big tank. But what happens if you don't have a big tank, you just have a small tank and you're feeding a pipe? Well, that would be a sudden contraction. Or you're going out of a pipe into a bigger tank, but now it's just a sudden expansion. So sudden expansion, sudden contraction. These you look at, they'll have curves for the loss coefficient depending on the diameter changes, etc. Okay? So there's no simple equation. Look in the textbook, get the right one. But you can get a loss coefficient for the sudden contraction and a loss coefficient for the sudden expansion. Right here you can see you'll get a lot of recirculation in this region. You're going to get losses. And here the same, you get that recirculation region in there, you'll get losses. Bends and branch loss coefficients. Well, the bends are the elbows. So you're coming along, it does a 90 degree and it turns. Now you could come along and have like a mitered 90 degree, hard to do in a round pipe, easy to do in rectangular ducts. If you have a rectangular duct, most of the time they like to just miter those, not try to do a, let's think about square duct doing a nice smooth bend. They don't typically do that. Typically it's mitered. So you think about it, maybe I show it showing some dimensions on there. That's what they mean by mitered. It's like it's cut at a 45 and put together. Let me just show this as like that. Okay. If it's round, it's a lot easier. Well, this would be a 90-degree elbow. Okay. And the elbow, you can have what they call the nominal or the long radius elbows. If it's a long radius, then it's a smoother bend, a slightly lower loss coefficient. What you have to do is you have to look in the textbook to remind yourself of the values. They also depend on how did you join up this elbow with the other pieces of equipment. Was it threaded? Was it flanged? Was it glued? Now they're only going to put in here flanged. They're going to say the loss coefficient was 0.3 for flange. Was it threaded? The loss coefficient 0.9. What is flanged? It's here, and then they put the bolts through and bolt it. It's more common to have threaded in small pipe systems. Okay. How about with the mitered? Well, for a duct like that, 90-degree bend, they'll have a loss coefficient of 1.1. If you insert helpful little turning vanes, and yes, in the air systems, you can buy those, and the person that's doing the air duct work can install those turning vanes. And the reason they do that, they help the air navigate the turn, and the loss coefficient is reduced to maybe 0.2. It went down a lot. That's a big drop in the loss coefficient. One time in my house I had purchased, it was a split level house. We don't live it anymore, and the living room was down on the bottom, and one section was always hot. Not only was it on the west facing wall, so the sun in the evening in the summer, 9 months of San Antonio summer, but went up there and looked at it, and the ductwork, it's like this. The house was here, and you had a split level, and you had a front, and this was the west facing, so it got beat up with a lot of sun. And the air conditioning system was right here, and it came up to a main duct run that went down and fed the bedrooms, and then it had to transition and drop down, and so it went like this down to feed this one, and there was a kitchen over here, and it ran over here, and it did a mitered 90, and it went, and then it dropped down, and it fed the front living room. The front living room was always painfully hot, especially in 9 months of summer in the evening when you want to entertain guests in your living room, right? And so my poor mother, she called out the HVAC techs, can you come out and check my air conditioning system? It's really hot in this room. And the guy takes a thermometer, puts it up to the grill, and then he says, you know what? Why are you complaining? It's coming out nice and cool. Dribbling out nice and cool. It's dribbling out. Do you understand the difference? Yeah, it's coming out cool, but there's almost no flow coming out. The guy you have to put 2 and 2 together. You need a lot of the air that is cold, not just a little dribble of air that is cold. And when I went up there and I looked at it, this had been a very hard mitered 90 with no turning vanes. Nowhere else did it have any. It was just straight runs, no hard turns. And when you took a look at the equivalent diameter for that, it was like a 12-inch equivalent diameter, 1 foot equivalent diameter. All right. And then you have it mitered, and so then you have that loss coefficient. If you go back to the length equivalent concept, just to help you get in perspective, okay, what is the effect of just this one mitered 90 right up here with no turning vanes? You had friction factor, diameter, what was it? Is it K diameter, friction factor, right? So the nominal friction factor, I forget what it was, 0.02. So the nominal friction factor 0.02, the diameter was 1 foot, the loss coefficient was 1.1, okay? So this friction factor, that's 1/50th. You come up here, 50 foot of run. It was equivalent to 50 foot of run, the resistance on that one little turn. Do you see that? I put it in perspective. No wonder you got dribble out of it. And it doesn't help, too, that anytime anybody had to go up in the attic, the get up in the attic, you got up here, and if you needed to get down there, what did you just put your body over top of and sit down on when you were moving to, we had plumbing work. My parents had plumbing work, which they had to reroute some plumbing. And so the plumbers were up there. You think they care about the quality of the HVAC ducts? They're trying to get a plumbing pipe installed, right, in the attic. You get it something fixed. So they had to continually go from here over there. What do they sit on and crush with their hind end? That duct. So not only did you have that, you had a crushed duct. It's terrible. And if you ever go flex duct up there, you ever see any flex duct? It's always pinched. If you ever buy a house, and you will, you'll be rich, I know. Just throw out the flex duct. Tell them, I'm not buying your house if you have 1 inch of flex duct. Seriously, tell them that. Don't buy the house. You'll be paying for the rest of your life. And they'll put it in your house. Some codes in different states outlaw it. Texas, hey, we're free. We can do what we want, right? So we can gyp the customer. Don't get gypped. Seriously. Pay for the better duct. Tell them no. You're going to put in good ducts. Otherwise, you're going to have these hot rooms. Anybody been in a house or apartment and this room is uncomfortably hot? That's why.
That's exactly what they kept telling me.
Oh yeah.
I'm over there with the thermometer here, and then
Quit complaining.
20, 30
Yeah, you're getting.
You stay in here then and see how.
Yeah, especially on the west side, they need to dump more air in. They need to dump, typically you basically give so many CFM per square foot of living space. But if you're having the west side in any glass, you need more CFM per square foot of cold air. So all of this hopefully makes it more real to you. Put in little turning vanes. They're not that expensive. Just put them in. It'll help. Also, if they don't put in the turning vanes, how is it going to separate? It's going to separate here, right? There'll be this whole region in here. And I think also there was a takeoff for a duct that went this way, one place. I think in my illustration there was a bedroom, and they took off right here and fed that bedroom. It was right after, close to the turn. You're not going to get good airflow to go in that leg. It's the wrong way to coming over after that 90 degree to try to go this way and have to feed the grill in that bedroom right there. So, but you know what? They're just going to put that up fast, right? They're just same neighborhood, the next door neighbor. He said, man, I had this bedroom. It was always cold, cold, cold in the winter and hot, hot, hot in the summer. So this was built in the 70s, same time our house was built. So about 1995, 25-year-old, 30-year home. He said, I'm going to add some insulation in the attic, and I'm going to do it myself. So he got up there, and this is all in the 70s. They had hip roofs, not the real tall roofs, so everything's tight. That's why the plumbers always sat on that ductwork, because they don't have any headroom. Now you go in a house, you could stand up and have a party. But in the 70s, everything was near these flat roofs, right? So he gets up there and crawls. He's got his rolls of insulation. He's working his way back there. He finally gets back to that bedroom, and he looks, and sure enough, in 1970, they put the insulation all over in the roof of that house, and they put the insulation in the back over that bedroom, right? And it was still in the rolls. It was just sitting back there in the rolls. Never cut, opened up, and spread in the, 2x4. For 30 years or so, 25 years at home, that bedroom is hot and super cold because of that. Some guys got off a couple hours early one day on a Friday, and they didn't finish the job. So when you have a house built, specify your ductwork and check up on the insulation and go where it's really difficult to go, or pay somebody to do it for you. It's well worth it. Let's solve another problem. So we have water at 5 degrees C. This density and viscosity flows in an 8 centimeter diameter. So the diameter is 8 centimeters. The length is 33 meters long. It has an average velocity of 5.5 meters per second. The piping system involves multiple flow restrictions with a total minor loss coefficient. So just sum up all the KLs, it's 2.6. And the friction factor, F, was 0.025. Determine the total head loss of this piping system. You want the total head loss. So the total head loss, H of L, is going to be the head loss major plus the head loss minor. I'm going to pause right there. No, I'm not. I can't. Don't have time to pause. I need to finish it for you. So what about the major? It's the friction factor, the length to diameter, V squared over 2G. The head loss minor, the loss coefficient, V squared over 2G. True? So we know this friction factor. We know the length. We know the diameter. We know the speed. G we know. The loss coefficient we know. The speed and G we know. True? So go ahead and calculate all of the loss coefficients. If I do the F, L over D, the friction factor 0.025, length 33 meters, diameter 0.08 meters to correct, get the right units there. This coefficient becomes 10.3. The K was 2.6, V squared over 2G. So you can see that in this case, the major losses still dominate the frictional losses, or the head loss. See that? Okay. That just gives a little insight as to which is dominating the head loss. And so it's equal to 12.9 times V squared over 2G. And when you finish it out, the head loss comes in at right at 20 meters. So that's the head loss of the piping system. Somebody says, what's the pressure loss? Multiply by rho G, and you'll get it. It's about 195 kPa, kilopascal. Make sense? Thank you very much for your attention. We're done for the day.